Okay, so welcome to your first revision lecture. Today we're going to be looking at epidemiology or pop health. Feel free to ask any questions in the chat or send me an email afterwards, or just raise your hand if you've got something to ask. I'll get going. So just a credit to PS Popper. A lot of the content is from there. Last year's revision lecture, and Akil for giving me the opportunity to present to you guys. Thank you very much.
Always here for you, Sean.
So what is epidemiology? It's the study of distribution and determinants of health and disease in populations. The application of the study to control health problems. Important thing to note, it's worth about 5 to 10% of one of your papers. It's not going to be worth spending 2 whole days on. I don't know. I don't have your rubric. I don't know exactly how much, but don't worry too much about it. Take some of these people's example. We'll move on. So we're first going to take a look at risk factors. So you've got 2 types of risk factors, necessary and sufficient. These are sort of 2 quite important things that you need to be able to distinguish. If something is necessary, it's required for the disease to be present, and the disease is never present without it. Sufficient, if it's this single factor alone is enough to result in the disease, and therefore, if the factor is present, the disease is always present. Here are a few different types of risk factors. You've got modifiable and non-modifiable. So these ones are, as you would know, modifiable thing would be things like lifestyle factors, and non-modifiable would be things like genetics. Predisposing factors, so these are things similarly, they're already present, and you've got disabling and enabling risk factors. Disabling assists with development of the disease, and enabling improves or aids with recovery. Precipitating, which is directly linked to the outcome, so you've got your exposure to the disease agent. And reinforcing risk factors, which are sort of those which repeated exposure causes reinforcing sort of, exposure, I guess. Next, we're going to look at the Bradford-Hill criteria for causation. So what this is it's a set of criteria which needs to be fulfilled in order to establish causation. It's important to note that just because there's correlation, obviously, as you would know, it doesn't necessarily mean there's causation. The most important thing of this criteria is temporality, and that is the cause must come before the effect. Obviously, something can't cause something else if they happen at the same time or if it happens afterwards. Similarly, plausibility, it must be consistent with our prior existing knowledge or what we already know. Consistency, which is different because it's whether the studies have similar results. Strength of association, so it's how much sort of correlation there is between the 2 effects. Dose response, so if you increase the exposure, does the effect increase as well? Reversibility, does removal of the exposure or the cause a removal or reduction in the effect? And the strength of the study design, which will be more pertaining to the actual study itself. Next up, I think we've got a couple of questions. Just throw your answers in the chat. I feel like a Twitch streamer. If you got any answers, any takers? Okay, yeah. So for you saying B, yep, the answer is B. Someone said it was C, but the reason it's not sufficient and necessary is because you can have the Mycobacterium tuberculosis. About, I think, 20% of the population has it, but they don't actually have the infection itself. So therefore, it's necessary. You need to have the pathogen itself in order to get the infection, but you can have it without actually getting the infection. Next up, trisomy 21 is blank for Down syndrome. Yep. Okay, I'm getting lots of C's. Very good. It's sufficient and necessary. If you have trisomy 21, you will, no matter what, you have Down syndrome, and that's the only thing required as well. So most prior studies to date have demonstrated a positive link between alcohol consumption and risk of liver cancer. Which criteria would this fulfill? Okay, so this is the important distinction between plausibility and consistency. So the answer, yes, is C. With plausibility is more about your existing knowledge. This is specifically pertaining to other studies that have been demonstrated, and so this is consistent with those. Next up, we're going to look at some metrics to measure disease. We've got mortality, which is number of deaths in a population per unit time, so deaths per year. Case fatality specifically refers to deaths within a particular disease, so it's the deaths per number of cases, cases being the total number infected or individuals infected. Morbidity refers to, it's a combination of quality adjusted life years and disability adjusted life years. So it's a measure of who is living with the disease. So it takes into account both years of life lost and years lost at disability, and it's a weighted score. As well, person years, it's a measure of the time at risk in years of people that contributed to the study. So say, 5 people contributed to the study for 5 years, the total person years there would be 25. Next up, we've got prevalence and incidence. The important distinction there is prevalence is the number of people with the disease at a specific point in time. It's definitely more useful for chronic conditions, whereas incidence is how many people develop the disease. And here you've got specific metrics such as prevalence, which is the total number of people disease divided by the population at risk, while cumulative incidence is the number of people who develop disease over the population at risk. So it's normally measured in a specific time frame. Again, prevalence is more useful for chronic conditions. Incidence is more useful for infectious diseases. And incidence rate is a measure of incidence, but relative to person years. So you do it in number of person years at risk of getting disease. And this is just sort of a quick summary. I don't think we have time to fly through every one of these. So I'll just go through I've gone through the more important ones. I think we've got a few questions. So how would you calculate the prevalence of high blood pressure for women at the age of 65? Exam questions are probably going to be more similar to this in the sense that they are multiple choice and they won't necessarily make you calculate. It could be so how would you calculate the prevalence? The answer is yeah. Getting lots of C's. Again, that's correct. So you add the 100 and the 300, and that is your total prevalence. And how would you calculate the incidence rate? So that's the one in person years, assuming that everyone who developed high blood pressure on average developed it at the end of 5 years. Okay, I'm just gonna move on to the answers. It's this, because you got to take the 300 who developed blood pressure, and you divide it by the 300 multiplied by the 5 years on average it took, and you add the 1600. This could be a mistake in the question, actually. I'll get back to you on that one. I'll move on, sorry. That could be a mistake in the question. So next, we're just going to move on to some definitions of risk. Here you've got your relative risk, which is the risk in exposed versus the risk in unexposed. Here, the important thing, I guess, later we'll distinguish between relative risk and odds ratio. Those are two things which could be confused. Risk is you're comparing the exposed to the unexposed. Attributable risk is the difference in the risk in exposed and unexposed. The attributable fraction is the risk in exposed subtracted from the risk in unexposed. So it's the risk difference over the risk in exposed. Whether this is as a percentage, so the percentage of cases specifically attributed to the exposure. Here you've got your population attributable risk, which is your total population risk subtracted from your risk in unexposed. So the percentage of the whole population, percentage of cases in the whole population that can be attributed to your exposure. And sorry, that's come up. Your population attributable risk percent, which is your population attributable risk divided, so total population minus risk in unexposed, divided by your total population risk. And this is also measured as a percentage. So this is the percentage of cases in the population that could have been prevented without exposure. So here's your odds ratio. This is normally used, important to note that in a case control study, and it's the odds that exposure is the cause of disease rather than the risk of those exposed versus the unexposed. So these two normally get confused. Here's just a formula to use to calculate it. I wouldn't remember it in A, D, B, C. I just remember what the values are and what they mean. So it's the odds of being exposed over the odds of being, odds of a case being exposed rather, versus the odds of a control being exposed. And if one, the odds of exposure amongst cases, or rather, if it is one, the odds are the same. If it's greater than one, cases is higher than control. And if it's less than one, then the odds of being exposed amongst cases is less than control. So yeah, can you calculate the relative risk between smokers and non-smokers? Yep, I'm getting A's, that's good. It's the risk in exposed divided by the risk in the unexposed. So how do we find the risk in exposed? You've got your 12 divided by, so of the people who are exposed, it's 12 over 20, because smokers are the ones you'd consider exposed, and the risk in the unexposed. So it's 6 out of your 30. How do you calculate the attributable fraction? So just a reminder, this is the difference between exposed and unexposed relative to the risk in exposed. Yeah. Okay, so again, this is, you take your difference and relative to the risk in the exposed. So it's C. And what's the population attributable risk percentage? So what this is, it's you take the population attributable risk, which is the risk in the total population, and subtract the risk in unexpected. unexposed, and you divide that by the total population risk. So yep, answer is A, as I explained, and this gets you the percentage of cases in population that could have been prevented without exposure. I think it's important that you guys know it as sort of what the numbers are actually looking for rather than formulas. Just try and get that learned. And how would you calculate the odds ratio here based on the exposure? So what is the odds ratio? It's the odds of the case being exposed versus the odds of the control being exposed. Yep, and the answer is D. And again, you can use the formula if you want, or you can sort of think it through and work it out. Moving on to the different types of sampling. Let's check. Here we've got, multiple different types of sampling. Simple random is sort of your most obvious random type of sampling. It'll be, something like rolling a dice and seeing and generating random individuals based on that. Convenient sampling, so that's based on what's, the most convenient. So, I'm standing in a mall and take the first 10 people who walk by. Voluntary sampling, which is I send out something for people to volunteer. They come and self-select. Systematic sampling, so that's sort of having a system such as every 5 people or every 6 people who walk by, or in a register, take every 6 people. Cluster sampling, which is dividing the population into clusters. So if I took, say, one of your anatomy groups, and I used that as a group. And stratified sampling, which is similar to cluster, but it's sort of, as you can see in this diagram here, it's more of an adjusted, you take a random, you divide people into groups, and then you take sort of a selection from each groups, but these groups are divided sort of to represent your demographic population so that your sample is more representative of the population. Here we've got different types of data. You've got your qualitative or your categorical. This is obviously sort of more categories and not numbers. So things like your blood type, which are nominal, where order doesn't matter, or ordinal, where order does matter, and it's, for example, cancer staging, or the other example I had was something like boxing weight classes, I guess, where the order does matter, but it's, again, categorical. Whereas you've got numerical or quantitative data. So you've got your continuous, which are normally your measurements, such as height, weight, etc., or temperature, or discrete, which are, it's a little bit more categorical. It's normally only integers or something like that. So things like shoe size. Here are your different types of error. You've got random error, which is errors due to chance, and this is reduced by increasing your sample size. So it could just be an anomalous result due to just random chance. And again, the bigger your data set, the less random error you'd have. You've got your systematic error, which is results from shift in your true values. This could be things like a measurement bias. So your machine is calibrated wrong, and you're getting constantly wrong results. Say it's overestimating by 0.5 or etc. Selection bias. So these are things like you've sort of selected a certain type of people, which may not be representative of your population, or perhaps they only fall into a certain category, and that could result in a sort of shift and error in your results. Or recall bias, which is things like people are more likely to recall sort of specific cases or incidents than if nothing happened. and that could affect or shift your results. And another type of error, which I guess is more contributory to random error, is if you have a too small a sample size and your results aren't a large enough data set. Another type of error or thing to take note of is confounding factors. I think they would have made a big deal out of this. So what a confounding factor is, it's when a outcome is influenced by a third factor. So just because, you know, there's correlation between your exposure and your disease. So say there's a correlation between alcohol and rates of lung cancer. But it doesn't necessarily mean that alcohol specifically causes lung cancer. It could more likely be that there's an association with a confounder, such as people who drink are more likely to smoke. And therefore, smoking is a confounding factor. And obviously, smoking is a direct risk factor for lung cancer. Lung cancer. How do we control confounding factors? It could be done at the design stage of your investigation. So by randomization and equal distribution of groups, restricting your participants to remove confounders, so you only get non-smokers in, or so that sort of removes the confounder factor, or matching your data or matching your groups for different categories such as age, sex, and social class. In your analysis, you could stratify your results by sort of having two tables for each confounder. So you'd have a table for smokers and a table for non-smokers. And sort of you can analyze those individually, and you get both results for both there, and statistical modeling just to sort of analyze those results as well. I think we have, yes, validating quality of research. You've got validity, which is sort of how does the test measure what it's supposed to. So I think these sort of images at the bottom here are a really good sort of just guide to figure if you haven't quite figured it out. So is it valid amongst the group being studied? That's internal validity, and external validity is how generalizable these results are to other populations. And reliability is the stability and reproducibility over time. So are your results consistent, or are they reproducible? Yeah, and sort of you can see in the diagram here, sort of a rough simplification of that. Just a few more questions. Sorry. Someone's asked if I could explain the second photo of valid but not reliable. So here, you sort of see that the results are averaging out to where they're supposed to, but your results aren't consistent, and you don't have a sort of repeatedly consistent sort of data set, and it's quite spread out. Next, just a question. Which of the following is an example of systematic sampling? Yep, easy. D. So what type of sampling is the first one? That would be probably cluster sampling. You're just picking out a random page of a group. B is asking your nearby neighbors. That's definitely convenience. And rolling a dice is simple random. Which of the following measures cannot be used to control for confounding factors? Yep, very good. You got a bunch of everyone saying C. Increasing sample size does reduce random error, but it won't help eliminate your samples. Won't help eliminate your confounding factors. Next up, we're going to look at the different study types. Note that these are observational, so everything from cohort studies down, and randomized controlled trials are what we'd consider experimental because we're actually influencing the results. I'll go through them case by case based on the lowest level of evidence. So you're starting off with your case reports and your case series. These are sort of singular cases or multiple case reports. They're normally detailed descriptions written by a doctor or team of doctors, and they help with identifying. They're really good at identifying a new rare disease. So something where you can't. It's a new thing. You would have to write about it, and you're just coming up with an initial report. It does help generate future hypotheses, but again, it's a low level of evidence. It contains little information and doesn't really often have a comparison group. Again, low level of evidence and low ability to analyze patterns. And it's susceptible to confounding as well as selection bias based on your cases. Next level is your ecological studies. Now, the most important thing to note is that this compares exposure and outcomes in populations rather than individuals. If you have any question, basically, which is asking about comparing different groups, it's almost certainly an ecological study. So, for example, death rates in each state in relation to smoking rates. So if you're comparing different states, again, you'd use an ecological study. What this does is it helps generate hypotheses, and it does manage to provide some link between exposure and outcomes. They're normally easy, fast, and cheap. The problem is, again, bias and confounding. It can establish associations, but it doesn't necessarily indicate causation. And data from a population level may not be applicable to individuals. So it's sort of because your data set may say this population has a high smoking rate and also has a high HIV rate, they may not be linked at all. And someone with HIV may not necessarily be a smoker. And cross-sectional studies. So these are a snapshot at a specific point in time. It looks at the prevalence and the presence or absence of exposure at that specific point in time. And you can use it to generate hypotheses about disease etiology. You can estimate prevalence of a specific outcome at a specific period of time. Again, relatively cheap, relatively easy, but it doesn't establish temporality. You can only just see sort of, if these people are cased or controls or infected or uninfected at a specific point in time. And it could be susceptible to recall bias if you're using, say, a point in time, which is in the past. You've got your case control studies. So what this is say, at a certain point in time, you take cases and controls, and you go back and find whether they've been exposed to something. Again, this is measured in odds ratio. That's quite important. And since you start with your outcomes, you can look at rare diseases. So I can find 10 people with a really rare disease and use them as my cases. Whereas if I do a cross-sectional study, it's much more difficult to get a group of population which would have as many people with that said rare disease. It's relatively cheap and relatively quick as well. And you can evaluate multiple exposures because you look at different cases and say, were you exposed to this, were you exposed to that, et cetera, et cetera. Your disadvantages here are, again, susceptible to recall bias, as well as selecting a control group, which, say, rather than 10 random people off the street, they have to have perhaps some exposure or something which could potentially or correlate to them being infected, but they haven't been. So the selection of your control group is sort of a difficulty there. Next up, you've got your cohort studies. These can be both prospective and retrospective. And this is measured in relative risk or your risk ratio. What you do here is you follow participants through time to see if exposure leads to different outcomes. So you can, if it's prospective, you take a group of participants, you follow them through, say, 5 years, and you see if they've been exposed to something or if their past exposure has led to different outcomes. So this is of your observational studies, going to get you your highest level of evidence and sort of best information about causation. It's your next best alternative to a randomized control trial if something's not ethical. Say you are exposing them to something potentially hazardous and you figure a randomized control trial is probably not best. And it's good for rare exposures and common outcomes, and good for studying multiple outcomes from a single cause. So say, and your problems with your cohort studies is that over a long time, it takes a while and you lose a lot of people to follow up. So some people may not return. They may join the studies in the beginning and may not return. And over the course of, say, 5 years, people's behavior could change. And that would also potentially affect your result, both individual behavior as well as sort of across a population level. Again, it's expensive and time consuming, and you could potentially have selection bias when it comes to selecting the people who participate in your study. Again, here you've got your difference between your prospective and your retrospective. Retrospective, you're sort of, you take people who were exposed and you look back. It's sort of in the past, right? You look back to see if they were, if they developed the disease, whereas prospective, you take people who were exposed and you look forward to see if they do develop the disease. Next up, we've got our randomized control trials. If anything says gold standard, you immediately think randomized control trial, because this is the highest level of sort of the experimental trials or studies. This is the gold standard. It involves random allocation and allocation concealment and double blinding, so that neither participants nor investigators know about the exposure. And this eliminates any bias or confounding. And it's notably free from unknown, or should be free from known and unknown confounders. Your notable disadvantage here is it could be unethical rather, or be impractical. Here is a really good example of what double blinding is. So the participants, as well as the investigators, don't know if the person has a placebo or an actual thing. And here you've got random allocation to exposed or unexposed. So it would be a placebo or they actually get the drug. And again, you look at the outcomes. So again, this is the gold standard, most probably and you've got your meta-analysis or a systems review, which is sort of a combination or analysis of previous randomized controlled trials or previous tests. This sort of congregates all the data together and allows for really powerful estimates or evaluations. Now, what study design is this? 20 infertile and 20 fertile men were asked about their previous usage of anabolic steroids. What do you think this is? Yep, really good. It's a case control. You get 20 cases, 20 controls, and you ask them about a past exposure. A group of women were asked about their oral contraceptive use. The occurrence of breast cancer in the group was studied for the next 10 years. What is this? Yep, it's B. It's prospective cohort, because you are going forward in time. You have the exposure, and then you follow up for the next 10 years to see if the disease develops. Next up, an epidemiologist is comparing the effect of COVID-19 on inner city populations in different cities. What is this? Yep, again, comparing different groups, always going to be ecological. Next, we're going to look at sort of more onto biostatistics. We're going to look at the distribution of data. Sort of just remember these curves. So which ones are negatively skewed or positively skewed, and what that effect that has towards the mean. So the way to remember it sort of is where the outliers are. Your mean will always be dragged towards your outliers. So in a case of a negative skewed graph, you've got a lot more outliers sort of at the lower end of whatever you're measuring, and that drags the mean backwards. And just sort of remember that in a left or a negatively skewed, the mean is less, and on a sort of positively skewed, the mean is greater than the median. You just sort of have to know that really for that. So now we're going to look at sort of things relating more to biostatistics specifically, things like confidence intervals. So this is a range around your sample where the population is likely to lie. So normally we use 95% confidence intervals. So that means that we're 95% sure that, or we're sure that 95% of the population falls between these two limits around our, say, if you have a value of, say it's an odds ratio, you'll give a range, and 95% of the population would fall within that. And if you're using a difference between two means, say the odds ratio of this is sort of 1.1 to 1.5, and the odds ratio of that is 8.3 to 9.4. If 0 is not included within the interval, so if 0 is not included between the difference, rather, there is a notable difference between the two results. So if there is no overlap of the two confidence intervals, then there's a notable or observable difference. What your p-value is it's the probability of an observed result being by random chance. So this normally follows a result, and sort of it's just the lower the p-value, the greater the significance of the observation. These things, I don't know how likely they are to be tested in isolation. You sort of just have to get a rough understanding of them. Here we've got hypothesis testing. So what this is, it's a hypothesis test is a test to assess the probability that a result would have arisen if the true result was something else. So what you do is you've got your null hypothesis or your alternative hypothesis, and you perform a statistical test, and say if you normally use your p-value of less than 0.05, and if it's less than that amount, you reject the null hypothesis. So that's normally something with a 95% certainty, I believe. And similarly, if you reject the null hypothesis, you accept the alternative hypothesis. And then your two types of errors are your type 1 error and your type 2 error. Type 1 is a false positive. So it's, telling this, say he's a cis male, that he's pregnant, which is probably unlikely. Well, yeah. And here you're telling, a cis lady who is clearly pregnant that she's not. That's a false negative. So you're accepting the null hypothesis when it is in fact false. I'll move on. Now we're going to look at different types of statistical tests. What you have to know is sort of what these are used to test for. So importantly is your two-sample unpaired t-test, or two-sample or your unpaired t-tests. These compares means from separate groups, such as the mean heights of females and males. Whereas your paired t-test tests for two variables in the same group or in the same population. So that's a distinction to make between there. Two-sample is two different groups, and a paired is two within the same group. So cholesterol levels before and after. These tests are all used for continuous or like continuous data. So they're used for averages and means. You've got your correlational tests. Sort of a simple correlation test is just to test the association between two continuous variables. And you've got your chi-square test, which looks at the strength of association between two categorical variables. So this is another important one that they may test you on. Just note that it's two categorical variables, so relationship between blood type and HIV, something like that. So statistical tests are, or rather regressional tests, sort of. This is more, not so much a test itself, but it's more of an analysis method where you've used to show relationship based on your results. So linear regressions, you'll plot your chart and you make a line of regression to sort of see if there is any correlation. And the closer the correlation is to 1, so the R value is a measure which is sort of estimating the average different distance to the line of regression, or how good a line of regression is. And the closer it is to 1, the stronger your correlation. And again, this is used for continuous data. You can use for single or multiple variables. And an example would be establishing the relationship between sort of rotation of movement, height, and gender, or your shoulder rotation movement. Oh, you guys wouldn't have done this one, but that was a practical that we did last year. With logistic regression, it's not that important that you understand how this works, but it's sort of used to test how a predictable variable predicts an outcome that is binary in nature, so it's one or the other. Again, a categorical outcome. So it's like an association between breast cancer, breast reconstruction, and whether the patient has private health insurance. So that's sort of two binary things. So now we're going to look at the different types of errors. Just a few questions. What do we think this is? What type of error has been made here? Okay, so people are saying B. It is, yep, you're correct. It's a type 2 error. It's a false negative. So people think there's no difference. So they've accepted the null hypothesis, but that is in fact wrong. There was in fact an improvement. So that's a type 2 error. Next up, you want to compare the mean blood glucose in 2 groups of men randomly assigned to groups of men assigned to 2 random groups in a clinical trial. What test are we using? Yep. Okay, so we are using a 2-sample t-test. Again, this is important. You're distinguishing between 2 groups versus comparing. Sorry, you're comparing between 2 separate groups rather than comparing 2 different variables. Correlation and linear, the difference between correlation and linear regression. I think, I could be wrong, they're quite similar. Linear regression is just more of an analysis thing to sort of establish correlation. I could be wrong. I'll get back to you on that though. If you want to, just drop me an email and I'll give you a full answer. Next up, statistical tests. So there's been an outbreak of gastro, and a case control study is being conducted, looking at different foods consumed by different attendees and the link to the outbreak. What statistical test would you use here? Yep. Again, for a case control study, you're going to use your odds ratio. Relative risk is used in your cohort studies or your RCTs. Odds ratio is used in your case control. I think we're approaching the home stretch soon. Next up, we're going to look at your outbreak investigation. I'm sure after this year, we're all quite familiar with this. Outbreak, or your epidemic, which is a more than expected number of cases in a group or a particular area at a particular period of time. A point source epidemic is where susceptible individuals are exposed simultaneously to a single surface of infection. So that could be a gas leak on a specific moment at a specific time, and everyone is exposed to it simultaneously. A pandemic, that's sort of an epidemic on a global or an international level. Clusters are a group or a collection of cases, normally limited to a specific geographic area. And an endemic, or rather endemic, or something is endemic, it's sort of a relatively stable disease incidence or pattern in a particular area. So say an area has particularly like fixed levels of, even though it may be high, it has sort of fixed and stable levels of malaria, and that would be sort of a malaria endemic. Here we've got your outbreak investigation and the disease natural history. Here is just a graph of these specific terms, and you can sort of see this is your latency period, which is the time from when you're infected to when you become infectious. Your sort of infectious period, where you are able to transmit the disease to someone else. And here you've got your incubation period, which is the time from infection, the time from when you become infected to when you become symptomatic. So this is separate from your latent period. One is till you're infectious, the other is till the onset of disease, and your symptomatic period is time from when you show symptoms until either you recover or you don't. Here we'll be looking at outbreak investigation, a few more definitions. So your index case is your very first case in the population, but it may not necessarily be identified. Your primary case, I've not put anything there, but your primary case is your first identified case. Important that this one is identified, which distinguishes it from the index. Secondary cases are cases after that. I'll put in a definition there. So any case subsequently infected. Your reproduction rate is the average number of cases generated by a single case over the infectious period. So say one person, how many people on average a single person infects. So if it's greater than one, this disease continues to spread. If it's less than one, you've got some mitigation, and you'll eventually see a decrease in cases. And immunity is the capacity of an individual to remain free of infection after exposure. This could be due to a series of things, such as, you've recovered from disease and you're no longer susceptible, or you have been vaccinated. These are the different epidemiological curves. It's important to note the difference between the three. Here's your point source. You sort of see a steep upslope after maybe an initial sort of peak, and then you'll see a huge upslope and a more gradual downslope. A continuous source, it's more across a wider period of time, and it will plateau corresponding to the duration of the exposure. So say this in 3 days or 4 days, and it'll sort of plateau onwards from there. Here with your propagated source, this is when your disease is transmitted, and your curve will look like the peaks in your curve will sort of be separated by incubation periods. So say it takes 3 days to be able to spread it, or 4 days or whatever, and you can sort of see that here this person's been infected but hasn't spread it, and then once the incubation period is over, then you see another increase in spread, and after a few more days a further increase, and so on and so forth. Here we're looking at diagnosis and screening. The difference between a diagnostic test and a screening test. One is investigating symptoms. So
yeah, someone's come in and asked, oh, I'm not feeling well. I may have, say, diabetes, and you go and test to investigate whether they have diabetes. Whereas a screening test would be something like a pap smear, or where it's on a, or a colonoscopy, where it's based on a, you know, healthy population, and it's just a screen for the disease. Okay, so here's something quite important to note and understand, which is the difference between sensitivity, specificity, positive predictor value, and your negative predictor value. What sensitivity is, it's the proportion of people who have the disease that test positive. So that's your true positive over your total people with disease. Specificity is the proportion of people without the disease that test negative. Your true negative over your total without disease. Positive predictive value is the proportion of positive tests that have a disease. So it's, if I've tested positive, what are the chances that I actually have the disease? And similarly with negative value, it's, if I've tested negative, what are the chances that I don't have the disease? A lot of people teach this or remember this with the sort of grid and the ABCD or whatever. I don't recommend that. I think it's definitely much easier to actually learn these definitions, and you can sort of figure out from there. So here, sensitivity is, again, proportion of the people who have the disease that test positive. So of these people who actually have the disease, how many of them have tested positive? And similarly with specificity, how many of the people how many people who actually have the disease have tested negative? So here we've got a few questions. First, we'll look to calculate the sensitivity and specificity. So just throw a few calculations in the chat for that, because I think this is important. I think I won't give you multiple choice for this one. So again, what is sensitivity? It's the proportion of people who have the disease that actually test positive. Yeah. Okay, that's good. So your sensitivity is the proportion of people who actually have the disease that test positive. So you're 40 out of 50, right? So because 50 people actually have disease, 40 of them tested positive. Similarly, specificity is the proportion of people who don't have the disease that test negative. So there is your 75 over 100. And now let's look at the positive and negative predictor values. Someone's got them down. Yeah, so what are the chances that I've tested positive? And if I've tested positive, what are the chances I've actually tested positive? So you divide 40 over your 65. And what are the chances that if I've tested negative? Okay, this should be a 75. This is wrong. I'll correct that. I've tested negative. What are the chances that I'm actually negative? So it's 75 over 85. I'll correct that. Yeah, we'll move on. Next, we're going to move on to your WHO screening requirements. So these are sort of guidelines or requirements issued by the WHO for how screening should be conducted. Your disease must be well-defined or with a known prevalence. There must be a long period when disease can be detected and when it presents. So there's no use in spending a lot of money in screening if you're going to find out within a week or so anyways. And it has to be serious and treatable. There's no use in screening for a disease if it's not treatable, because there's nothing you can do, sort of. Your test must be simple, safe, effective, cheap, and it must be sort of equitably accessible. Here's just distinguishing between length and lead time bias. So your lead time bias is your apparent increased survival due to an earlier detection, but the disease course is unaffected. So survival appears longer, and length time bias is apparent increase in survival due to screening detecting cases caused by relatively slow progressing cases rather than sort of short, more serious cases. And this overall results in overdiagnosis. You can see here sort of the difference. Your lead time bias is these people, your early diagnosis doesn't actually affect it or doesn't affect the progression to disease. It just makes it seem like survival is longer because you've identified it earlier. And here is sort of a diagram just to illustrate how sort of length time bias may work. Here you've got your different levels of protection or prevention rather. Primordial, which is targeting your determinants of health. Primary prevention, which is targets healthy individuals. Secondary, which is your sort of early detection of disease and prevents further development of disease. And tertiary, which is to alleviate disease consequences. So it's sort of your management. I've just got one more question here. So which of these is the correct sort of level of prevention? Yep, your correct answer is B, where you've got your taxing cigarettes, that sort of looking at more macro sort of determinants of health point of view. Dumb ways to die, sort of an information campaign. Biannual colonoscopy, that's your screening. So screening will always be under secondary. And dialysis is sort of management style tertiary prevention. Yeah, do we have any questions? I think we are nearly out of time. But thank you very much. Please feel free, that's just my email. Send me any emails you have. There was one we got to earlier, which I'll let you know about. If not, let me see if the next lecturer is here.
Yeah, I'm here, Sean.
All right. Do you want me to, let me stop recording.